And we had a little bit of conversation. So I hope that you followed up the previous lectures. They are available on YouTube, by the way. So if you have any questions, please ask me after the class or during office hour, which is Thursday. By the way, I was there on Thursday and no one showed up. Only I think a person with the name of Henry clicked on the link, but he did not wait, I think. So anyway, let's start the lecture. Let me see what we have finished last time. I think we finished somewhere at, okay, so we got something like vector potential, which was this. So we found out that A of R and T is given by summation over all k vector and sigma, which is the polarization. Then we got AK, E, K, and sigma. And then we had two terms. Essentially, one is a complex conjugate, the other one. Let's write it in Heisenberg picture in such a way that the operators are time dependent. So let's write them in this way. It still is not operator, by the way. It's just a parameter that we have it for the quantization. So which was A of K and sigma, time dependent, x power of I K dot R. And the other one was plus A star, then K and sigma of T, e power of minus I K dot R. If I remember well, this was the condition that we got. All right. True. Okay. And then we say that the operator is time, and this parameter is time dependent, and we replace it inside of wave equation, which we got it for vector potential. Just to briefly review that we found the sigma that will take the two values of 1 and 2, and this sigma has a property which means that the vector that we have E of K and sigma, they are orthogonal to each other and they are normalized to 1, so it's given by delta of sigma and sigma prime. And on the other side, we say that A is the parameter that defines the amplitude. We will find this explicitly. It's not given in your book, by the way, but we will find a way, the analogy that and the analog that we have, and we find the reason why in the books they have that term, that explicit term that we'll drive at the end of this lecture. And A, K, and sigma T, we say that when we replace it inside the wave equation, what we will get for A and T is a derivative of A of K and sigma with respect to time is given by minus I omega A of K and sigma and time. Good. All right. So this was from wave equation, which was Laplacian minus 1 divided by sigma c squared time derivative of A of R and T equal to 0. And remember that omega had a relation with K. So omega essentially divided by C was K. So it is good to note for ourselves that omega is K dependent. So we place a K here just to remember that omega is a function of wave vector. Good? Excellent. And remember also from the divergence of A equal to 0, which came from the gauge, choosing the proper gauge. Remember that that was under the condition that divergence of A was 0. And also we assume, since there is no charge and there is no current, we assume that phi is 0. Then from the divergence of A to be equal to 0, we found out that K dot sigma of K, E of K and sigma is equal to 0. Okay. I think that's a simple expression that we found last time. All right. And as an exercise, I asked you to drive the proper equation for E from these expressions. Good. So E if you remember, was minus time derivative of A, and B was curl of A for this expression. Okay. So this was the way that we found electric field and magnetic field from potentials. Since scalar potential by choosing the gauge was 0, then we got this expression. So, all right, how many people they did the exercise? No one. Cool. Okay, let's do it together. I will do it for E, and let's see what we can do it for B. I will give you a hint for B as well, but I will leave it to you to do the mathematics. Okay, let's do it for E. Here, let us calculate E from A, vector potential. So E essentially is given by minus time derivative of A. So it is given by minus time derivative of A, which is summation over K, summation over sigma. Sigma is 1 to 2. And K, remember that that was another exercise. K goes from minus infinity to plus infinity. And then we have a K, all right, E of K and sigma. Then we have A of K and sigma, E power of I, K dot R, plus A star, K and sigma, E power of minus I, K dot R. Okay, so that is the expression for electric field from vector potential. So which terms are time dependent? Sierra. Which terms are time dependent?
Time dependent. AK.
So, this is not time dependent, right? Because it is only coordinate dependent. That is the same story. E also is not time dependent. AK also is not time dependent. The only term that is time dependent is A, right? Okay, excellent. So we know that A is time dependent. So the derivative will act only on A. Then what we will get summation over K, summation over sigma, AK, E, K, and sigma. then we do have the time derivative of this, which is dt of a, k, and sigma of t, e power of I, k dot sigma, dot r, sorry, plus d dt of a star of k and sigma, e power of minus I, k dot r. All right. And remember, the derivative acting only on the first term, which is this one. So let me ask someone
There's
else.
a minus sign?
Pardon?
Is there not a minus sign missing?
Oh, there's a minus sign here, yes. Thank you. Philo, since you speak out, so can you tell me what is this term? You are muted.
It's what we wrote above.
Exactly. So that will be minus I omega k a of k and sigma of time. What about that one? The other one?
Positive I omega?
Exactly. It will be complex conjugate of that. So the complex conjugate, so it will be positive I omega k. Josh, tell me the rest.
Well, it's AK sigma complex conjugate.
Exactly. What is important that you have a complex conjugate on this as well. Okay? Fantastic. Remember, summations are on sigma, which is polarization. So it counts for two types of polarizations, which is let's say polarization number 1 and polarization number 2. And also k is from minus infinity to plus infinity. Okay? Good. Then if we simplify this, we will take away the minus sign. So it will be summation on k, summation on sigma, ak, omega k. I will take away omega k as well. I have I as well. I factor out I. Then the first term will be a, k, and sigma t exponential of I, k dot r minus a, k, and sigma t star of e power of minus I, k dot r. Okay? This is the electric field. Note that omega k cannot go out of the summation because it's a function of k. Okay? I cannot take away the omega. Do you have any question? Okay. If I want to write it in Schrodinger representation, what I have to do? Do you agree this is a Heisenberg picture? A of k and sigma is a function of time. So this is a Heisenberg picture. Okay? Which again, what we found, it was dA dt was minus I omega k ak. In the Schrodinger picture, what we have to replace that with the time dependency. So in the Schrodinger picture, we have summation of k, summation over sigma, I, ak omega k, A of k and sigma at the time of 0, all right, e power of I k dot r minus omega t plus, oh, sorry, minus A star of 0, k and sigma, e power of I k dot r minus omega t with a negative sign. So that's a Schrodinger picture. Oh, there is an epsilon I, which is E of k and sigma, which is I'm missing. Here also I have E of k and sigma. Okay. This is electric field. What about magnetic field? We have to take the curl of A. Remember the electric field, I will be using it, okay? And remember magnetic field also, we will drive the magnetic field, but we have to make a note of the explicit expression that we have for E and B. So magnetic field instead is given by curl of A. So that means that I have to take the curl of A, which is summation over K, summation over sigma. Then I have A of K. I have E, K, and sigma, which is a unit vector. Then we do have A, K, and sigma, e power of I, K dot R, plus A star of K and sigma, T, e power of I, K dot R. All right, I have to take care of this. Mahta, can you tell me how, when I'm taking the curl, so curl essentially is given by x hat derivative with respect to x plus y hat derivative with respect to y plus z hat derivative with respect to z. That's a cross product with a vector. So what is the action of a curl on A? It acts only on which term?
Well, okay, hold on a second.
Sure.
Well, it will act on the ones that have R on them.
This term and that term.
Yeah, yes.
Exactly, excellent. Thank you. So then the action of this, if you remember from classical optics, classical electrodynamics, I think I proved that even for undergraduate level. So the action of a curl on a plane wave will be given by I, K, right? And action of time on a plane wave will be minus I omega. Okay? So let us do the mathematics here. So for the first term, what we will have a summation of K and summation of sigma, AK. For the first term, we have a positive K, so the action will be IK cross E, K, and sigma. Then we do have AK and sigma e power of I, K dot R. minus I k cos E of k and sigma A of k and sigma t star e power of minus I k dot r. Okay, clear? So essentially, the curl of that term will be replaced by ik or minus ik, depending on the term, but we have to respect when it starts. So from the left side or from the right side. That's the reason that you have a cross product with ek in both sides, so in both terms. So this is essentially your vector. We can simplify further. So in order to simplify further, we let's take away the k and sigma, of course. Then I have a with the I sign, and then I can take away the k vector unit. Then the k vector and e inside, there will be a unit vector. So that will be k hat cross e k and sigma. A and t of k and sigma e power of I k dot r minus k hat again cos e k and sigma a star of k and sigma e power of minus I k dot r. Okay. Again, remember that the summation is over k, so you cannot take away the k, take this k out of the summation. Be careful of this. It's very similar to omega that we had it for electric field. Good. Questions so far? For those people that they are interested to write it down in terms of Schrodinger's picture, then you will get k sigma I a k k k cos e k and sigma a 0 of k and sigma e power of I k dot r minus omega t, and then minus k hat cos e k and sigma a 0 star of k and sigma e power of minus k dot r minus omega t. Good. So that's the electric field and magnetic field that we obtain from vector potential. In some book, they write it differently, which at the conclusion, we will drive them in a form that usually you see them in the textbook. Okay, good. So we have electric field and we have magnetic field. Why we drive this? I mean, if we look at the story that we had, we say that let's do the field quantization. We start with the wave equation for vector potential, and we try to look at those photons that they are propagating forward. So we assume positive and negative energy as well. And then what we got electric field and magnetic field from them, with the condition that there is somehow an operator in our calculation, which is time dependent. And this is what we obtain. Now, since usually we start with Hamiltonian, and analogous of Hamiltonian in the classical mechanics is the energy that we usually have. So I'm asking you, can we drive what is the Hamiltonian for electric field and magnetic field, or essentially what is the energy of electromagnetic fields. So this is the energy of EM field. Remember again that this is in vacuum. There is no charge, there is no current, okay? So what is the energy of electromagnetic field in vacuum in terms of E and B? Kilon? Tenglo, sorry.
Sorry, could you repeat your question again?
So what is the energy of electric and magnetic field or electromagnetic field in vacuum?
In vacuum, is there something related to pointing vectors? No, not really.
So let me help you, okay? So
Okay.
definitely we have to do the integral or the volume, okay? So that is very clear. So we have a energy per volume, okay? And energy per volume is given by 1/2 of epsilon 0 E dot E plus 1/2 of mu 0 B dot B. This was the energy of electromagnetic field. We had this in EM course and also in electrodynamics course. So you can obtain this essentially. And from this equation, usually they find the Maxwell tensor, stress tensor, if someone wants to look into deep calculation. But Tenglu, it is correct. Somehow this energy is related to the Poynting vector, okay? By a divergence and the time derivative. I'm not talking about that, okay? So then let's do this and find the energy, which is look like Hamiltonian for us for electric and magnetic field. So in order to do this calculation, we have to make the dot product of E with itself and B with itself, and then sum them up together. Let me simplify this equation a little bit. So if you take 1 divided by 2 out and mu 0, if you factor this, then you will end up with 1 divided by 2 epsilon 0. We assume it's vacuum, so I'm not really worried about being epsilon and mu. So it's constant, it's homogeneous. In vacuum, it can be taken out of the integral. So you have this one d3r, then you have E dot E plus 1 divided by mu naught epsilon naught, which is c squared, and this is B dot B. It's not surprise, right? There's no surprise here because we know that what is inside of this should have the same dimensionality. And we know that the electric field, of course, in vacuum, we are talking electric field is CB in terms of magnitude. And we had these for Riemann-Sieberstein as well, vector, if you recall. For F vector, we defined that in a same fashion. Good. So now the challenge that we have is finding E dot E and B dot B for the parameters that we introduced in the calculation. So essentially, we have to do E dot E, which is, someone must help me. E is given by summation of K sigma AK I omega K EK and sigma. Then I had A of K and sigma. Let me see which one is good. Okay, let's write it with the Schrodinger's with the Heisenberg picture. E power of I K dot R minus A of t of k and sigma, that is star, e power of minus I k dot r, dot product with itself. So which is summation. Not necessarily the summation is the same. So summation should be on different parameter because that's independent, two independent summations. So it is k prime, which is a new vector, and sigma prime. And then we have a k prime, omega k prime, e of k prime and sigma prime times a of time k and sigma prime e power of plus I k dot r. The position is the same because we want to find that for the same position at the same. And minus a star of time of k and sigma prime e power of minus I k dot r. Am I missing something or is all right everything? Let me look at the equation just to confirm. I k e, that's true. That's true. Okay, fine. All right. That is E dot E. There's a dot product here. So then the summation will be essentially 4 summations. K, K prime, sigma, sigma prime. I times I will be negative, minus 1. A k prime. Omega k prime. Then I have E k and sigma dot E k prime and sigma prime. Then that's all parameters that I have. Then I have 4 terms, which hereafter I have to be extremely careful with the orders of A and A star. Okay, I'm not allowed to switch them up because later on what I'm doing, I'm replacing them with an operator. So let's do the mathematics and write them down. So this is the coefficient that I have. And then I have this the summation or these 4 terms. It is that okay. So it is A, K, and sigma time A, T, K prime, and sigma prime e power of I k plus k prime dot r. The second term will be with a minus sign, minus a k and sigma time a star k prime and sigma prime times time, and sorry, function of time, and then e power of I k minus k prime dot r minus a star k sigma and time a of k prime and sigma prime of time e power of I minus k plus k prime dot r plus a star of k and sigma of time a star of k prime and sigma prime of time e power of I k plus k prime dot r. Okay, I have these four terms. Okay. In a similar way, you can find magnetic field as well. B dot B. But let's just concentrate on electric field. Do you have any questions? Is there any typo or mistakes in the calculation? Okay, all right. This is energy per volume, all right? So if I want to calculate the total energy, what I have to do? Let's ask someone, Thomas.
It's going to be integrated over space.
Exactly. We have to take the integrate over the space. So which is integral of d3r, or essentially integral of dr vector. Okay. So then I have to do the integral of d3 of r of E dot E. Let's ask Henry. Henry, can you help me and tell me, when I want to take the integral will act on what? Which term among those summations that I have, they are R dependent?
R dependents are the exponentials.
Exactly, which are this term, this term,
Yeah.
this term, and this term. Let's ask someone else. So now, do you agree, guys, that if we take the integral of E dot E over the entire of the space, the integral will act only on those four terms. So essentially what we end up with will be integral of E power of I k plus k prime dot r d3r, integral of E power of I k minus k prime dot r d3r, and etc. So let's ask someone else. Chandler, can you tell me what you guess as this integral? Your mic is muted. Let me do a simple, let's say, we are physicists. We love to simplify things, right? We don't want to go with a very complicated situation. Let's look at the only x term, okay? So if you look at the only x term, that will be integral of E power of I k 1 minus k prime 1, or plus k prime 1, x dx, from minus infinity to plus infinity. And remember that kx was 2 pi n divided by L, because we are solving these for a box of dimension L times L times L. Eric, can you help me?
Yeah, the integral, I mean, it's going to reduce to the field inside the box, because outside of the box is going to be 0.
Yeah,
So it's
so
gonna be from
essentially
0 to
that will be going to be 0 to L. All right.
And then the integral of that would be e to the I, all that's in that, over I k1 plus k1 prime, and that's going to end up being sine x sine something over
True.
some function, something to do with ln x over x, where x in this case is going to be k1 plus
Yes,
K1 prime.
exactly. You're totally right. If you look at because since you know that kx at the boundaries at 0 and L, they should be equal to 0. The same story happens for the k prime as well. Then that will give you L delta of k1 and minus k prime 1. That is always 0 because this is look like a periodic function. When you do the integral or from 0 to L, and the integral of 0 to L for a periodic function with these boundary condition that you have, it always will be 0, apart from the case when the two are identical with a negative sign. Then in that case, that will be given by z integral of 0 to L of dx, which is equal to L. So essentially, all of those integrals, they will be replaced. Sorry, that was a little bit tricky for you guys. My apologies. So it will be, since it's a three-dimensional case, that will be L power of 3 delta of k plus k prime and 0. So it means that everywhere will be 0, except the time that k plus k prime is equal to 0, which means that this can be replaced by L3 delta of k and minus k prime. Or let's say k prime is equal to minus k. This is useful, better for us. Okay, so this term will be L3 delta of k prime and minus k. That term will be delta of L3 delta of k prime and k. This is the vector. Remember, it's 3 deltas. That is also is L3 delta of k prime and k, and that is L3 delta of k prime and minus k. Good.
It ends up being delta because the k vector is quantized.
Yes, because we are solving
okay,
that for the box.
Yeah, thanks.
Yeah.
Just
Okay.
needed to make sure.
Okay. All right. Oh, now I have to take care of all of those coefficients together because this is a little bit tricky and you should learn it once. I mean, it is good to do the mathematics. So then what I have now is integral of d3 of r e dot e. Then this is given by summation over k summation over sigma summation over sigma prime minus 1 a k prime is equal to minus k. Since this is the magnitude, it will be the same for both of them. So it will be a k power of 2 and omega k power of 2. Okay. The other term, no, the other term is extremely important because that's a function of k vector. Then when you replace it, you have to replace it with a proper sign. So let's do that for all 4 terms. So times all 4 terms that we have. So the first one will be E, K, and sigma dot. For the first term, and of course L3 can be factored out, k prime should be replaced by minus k. So then it will be E minus k and sigma prime. Okay, for the first term, the summation over k prime goes away. Every delta will be replaced by either 0 or 1 when they are identical, okay? Then I have A of K and sigma of T, A of minus K and sigma prime, function of time. Then the second term will be minus, here K prime will be replaced by K, so it will be E K and sigma dot E K and sigma. I'm replacing it with itself, sorry, with K. Then I get a K and sigma T star A of K and sigma prime of time star. The other one will be minus. The same for the other one. So E K and sigma that E K and sigma prime. A of K and sigma with a star. A of K and sigma prime function of time plus the last term will K prime will be replaced by minus K, then it will be E of K and sigma dot E of K minus K and sigma prime, A of K and sigma star function of time, A star of minus K and sigma prime of time. Okay. No mistakes? So the only things that I have done, I'm replacing K prime either with K or with minus K. Good.
We can choose that A K equals A minus K, or does A just depend on the magnitude of K?
So because A is only function of the vector, sorry, the magnitude.
Okay, okay, makes
Yeah.
sense.
Yeah,
Thank you.
and omega also is a function of only magnitude of K.
Okay.
Okay, that's a reason that I did not consider that is minus K or plus K. Good. All right. Here is a little bit tricky. What is the outcome of E dot E? Is a scalar or is a vector?
It's a delta function, right? Scalar.
Is a scalar function. Okay, is not necessarily delta. Okay, so is a scalar function. So then I have to work out on these terms. Okay. And simplifying them further. Last time, Eric pointed out to me that, Ibrahim, hey, be careful. When you write E, K, and sigma dot E of K prime and sigma prime, you have to be very careful what you mean by having a dot product of these two equal to delta of K prime. So now let's see. I think Eric was right, but let's do a little bit of mathematics and see what we will get out of these dot products. So look at the meaning of this. So those dot products will tell you that, okay, I have sometimes a vector which is propagating in this direction. Look, we are still inside of this box of dimension L and L and L. Okay, so we are still talking about that box. Okay, then inside of that box, I have a vector of K is propagating, and then due to the transversality for A, I have two vectors orthogonal to these, which defines the, now you see it, defines the oscillation, the direction of oscillation for electric field and also for the magnetic field. So then I have two vectors of, let's call them EK1 and EK and 2. Now look, they are right-handed. So E1 times E2 is K. And it was one of your assignments that you have to look at the calculation and prove that E1 plus E2 is equal to K squared and delta function. Good. If you have another K vector, which can go in that direction, this is what I call it K second, then this is E second, or let's say E K second and 1, that is E K second and 2. They have to form this right angle. All right. Now, what we deal here in these calculations, for this term, I have no problem. For this term, also, I don't have any problem. What is the result of these two, Felix? E, K, and sigma dot E, K, and sigma prime. The K vector are identical. So I'm talking about the dot product of 1 and 1, or 1 and 2, or 2 and 1, or 2 and 2. Is a unit vector. So it should be equal to
1 or 0.
Yeah, either 0 or either 1. So which means that when they are identical, they will be 1. If they are not identical, they will be 0. So it means that they are delta of sigma and sigma prime. So the same story here is delta of sigma and sigma prime. All right. But I have another problem. The problem is these other two equations. What is the problem with these two equations, Felix?
Here I think we need a negative sign for the minus K.
Exactly. We have a problem with minus K. We have to find a relation between E of minus K and sigma prime, okay, with E, K, and sigma. Okay. Let me ask someone else. Haha, good. Whom should I involve? Kate. Hello. Sorry, you're auditing the course, but asking questions. Okay. So.
Oh, that's okay.
Fantastic. So can you tell me what is the direction of minus K?
Yeah, just opposite to K.
Exactly, minus K. What I know about E1, E2, and K, they should form a right angle, right?
Mm-hmm.
So assuming that I'm fixing EK2 to be negative direction. Oh, let's write it in a different way. So now I'm choosing E of minus K and 2 to be that specific direction. What it should be the direction for E minus K and 1 that forms a right angle.
Maybe
I'm
I'm
now
missing
looking
something,
for
but can
E
it-
minus K and 1.
Yeah. I mean, can it not be either the direction it's in right now or opposite to that?
It should be in the right direction. Exactly
In the
the
right
same
direc-
direction. It
Oh,
cannot
right,
be
yeah, 'cause
negative.
coordinate system.
So it will
Yeah.
be E of minus K and 1. Good. Then I found the relation. So E of minus K and 1 is equal to E of K and 1, but E of minus K and 2 is equal to minus E of K and 2. Do you agree?
Yes.
Excellent. So let's write it as a mathematics formula, a single formula for these. And I know that sigma will take the value of 1 and 2. So I will write this formula and tell me if this is right or wrong. Minus K and sigma is equal to minus 1 power of sigma of E of K and sigma. So set sigma equal to 1. That will be minus times minus 1 will be positive. Set it to 2, then it will be minus times 1. It will be negative sign. Good. Excellent. Thanks, Kate. So now, with this relation that we found out what is the relation between K vector and negative K vector, I found the relation between the E's, the unit vectors for them. So, Cecilia, you have a question, yes?
Yeah, can you please explain why EK1 and E minus K1 are the same direction? I didn't get it.
Which one?
EK1 and E minus K1. Why they are
Okay.
in the same direction?
So it is up to you. Choose one of the direction for E, K, and 2.
Okay, yeah.
Right, which is negative direction.
Yeah.
Okay. And then I know that E1, E2, and K, they should be orthogonal and right angle.
That's true, yeah.
Then the only direction that I'm allowed is that direction.
So it's our choice whether we can choose EK2 or EK1 in the opposite direction?
Yes, either of them.
Okay.
But the other one definitely will be in the same orientation.
Okay, got it. Yeah.
Clear?
Yeah, clear. Thank
Okay. Let me tell you there is a physics behind of this. So if you look at the back propagating waves, do you remember that we solved this for dielectric, right? We had the dielectric slab of dielectric, not in this course. In the past, we have solved these. When you have a slab of dielectric, when electric field is coming in, the orientation of electric field will flip, right? And then you look for the magnetic field in such a way that E times B will be equal to the back propagating waves. So this is exactly the same physics here. Okay, good. So now we do have, I'm looking at the first term. So the first term is E, K, and sigma dot E minus K and sigma prime. So what is the result of this? I assume that when sigma is not equal to sigma prime, that's a different story, but I can replace this with E of K and sigma times minus 1 times a power of sigma prime E of K and sigma prime. Then that can be simplified further. Let me just clean this up. I have minus 1 power of sigma prime. Then I have E of K and sigma. dot E of K and sigma prime. So what is the result of this?
Minus 1 to the sigma delta sigma prime.
Exactly. Delta of sigma and sigma prime. The same expression that we had previously. Guys, I'm sorry, I'm taking too much time on details because devils are in details, okay? So you have to really learn this sort of calculation, else you will have problems. Okay, good. Okay, so this expression now, I know that that can be replaced by minus 1 power of sigma prime. Doesn't matter, I will call it sigma because I know that when sigma is not equal to sigma prime, that will be 0. So I will replace everything with sigma. Okay, so it will be delta of sigma prime, and the same story here will be minus sigma delta of sigma prime. Excellent. Okay. Now the summation over sigma prime will go away and deltas will be replaced by 1, and every sigma prime will be replaced by sigma. Do you agree? So the summation over sigma prime will apply to this calculation, and let's see what we will get. Then we will get, for the main expression, we will get summation over K, summation over sigma, minus 1, a k power of 2, omega k power of 2, L power of 3. Then I have 3 equations, which should I collect them together? Okay, let's do that. Okay. I get minus A. I'm writing the second term and the third term first. K and sigma of time. A star of time of K and sigma. That should be the same sigma. Then plus a star of K and sigma, function of time, A of K and sigma, function of time. That's the first term. And that's the second term and the third term together. The minus sign is factored out here. And first term and the last term, they have negative 1 power of sigma. I have A, K, and sigma, function of time, A minus K and sigma, function of time, plus A star of K and sigma, function of time, A star of minus K and sigma, function of time. All right. Any questions? No. Can we simplify further? Nope. We cannot simplify further. This is what it is. Okay. Remember, this was integral of d3r e dot e. Do it as an exercise at home. I gave you the expression for B field, right? Which was K cross E. So if you look at the expression for B, which was this term. Okay. This was the expression for B field. And what you need to do, you have to do exactly the same calculation for B dot B. And then you have 4 summations. The only thing that you have to deal with after the integral, of course, if you do the integral on R, then you have again the same 4 formalism. Let's say we had it here, that K prime should be replaced by K or with minus K. And then at the end, you deal with the K cross E times E, K prime cross E prime, okay? You have to deal with this dot product. Then you have to expand them. And when you do the expansions, then you simplify. And what you will get exactly similar expression, which I will write it down. I will write it down for D3R C square B dot B. You will get this expression. K sigma minus 1 AK square C square K square L power of 3. Then you have minus 1 AK and sigma of time K and sigma plus A star of K and sigma function of time A of K sigma function of time. And then the beauty is here, plus minus 1 power of sigma A K and sigma T A minus K and sigma and T plus A star of K and sigma T A star of minus K and sigma T. All right. We get C squared times K squared. What is that? Exactly, Nazanin. Exactly. Thank you. Omega square of K. So essentially they're identical. Is it surprising to you? Arman? Is that surprising to you?
Not completely, maybe. Good. I don't know.
Tell me more why it is not surprising. I mean, completely not surprising.
I don't know, just like from a relativistic point of view that we saw, like we have examples where like in one frame you have an electric field and no magnetic field, in another you have the opposite.
Right. And energy of electric field and energy of magnetic field in vacuum, they're identical, right? They have the same magnitude. So this is the reason that we are not really surprised. Maybe the interesting part is that this part cancels out this part. One of them has a positive sign, the other one has a negative sign, right? And that's the beauty. So then the energy, which Hamiltonian or energy of electric field of EM then is given by 1 divided by 2 epsilon naught, which I have taken out already, of sum of these two terms, which is summation over k, summation over sigma of -1 times -1 is plus, then I get a squared omega k squared L power of 3. Then I get a k. The 2 also goes away because I have two terms of them. Time and sigma a of star of k and sigma plus a star of k and sigma a star of k and sigma. Okay.
I don't think there should be 2 stars in the last term.
What?
Should there be 2 stars in the last term, or is the second one
Oh,
not
yes,
star?
of course, it should be 1 star. Absolutely.
Okay.
Thank you. Is there anything? Yes, that is omega k squared L power of 3, which is the volume. And epsilon naught. Yes, the dimensionality also sounds correct to me. Good. And remember that A and A star, they are labeled by K and sigma. These are the only two parameters, okay? All right. I will replace these with volume, guys. L3, right, is the cube that we had it, is the volume of the cube. And then I have a K sigma time A star. K sigma. Excellent. So I found the energy. In terms of the parameters in Heisenberg picture. Now, energy, since I mean it's very obvious from this expression, the energy at the time of t equal to 0 is equal to energy at the time of t. Can you prove these?
By looking at it in the Schrodinger picture?
Yes. Victor, can you tell me?
Well, it's what he said, right? So you get a naught and then e to the
yeah,
minus wt.
Yeah, here we will have e power of I omega t with a negative sign, and the other one we will have e power of I omega t with positive sign.
You can factor it out, right?
Yeah. So then those two, they will be almost independent of the time, the product of these two. Okay. So then it means that the energy is conserved, which is not surprising to us. It's in vacuum. Good. So I will hold this expression, and that I call it the Hamiltonian that we found, or energy that we found for a volume of V when we have electric field and magnetic field. I need to refer to these later on, okay? All right, so now we will have a break of, let's say, 10 minutes, 10, 12 minutes, and we will come back with completely a new subject, which is simple harmonic oscillator. We are not dealing anymore with these electric field and magnetic field. All right. Okay, so I will stop it here, and we will recording. Okay, good. I hope that you enjoy the short break. So now we found the Hamiltonian energy for electric and magnetic field for that specific case of a cube with the dimension of L, L, and L. So, and now what we do, we start to look at the harmonic oscillator. So if you recall, harmonic oscillator, that is simple, that's a break. We want to review simple harmonic oscillator. And then I think we learned this during quantum mechanics course, that this is the first thing that always we solve in classical mechanics and quantum mechanics. So we take the Hamiltonian for a simple harmonic oscillator, which is given by p squared divided by 2m plus 1/2 of k x squared, or let's write it in a general situation, q squared. And then we assume that k is equal to m omega squared, and this is given by p2 divided by 2m plus 1/2 of m omega squared q squared. Okay. And we know that in quantum mechanical language, these two are operators. So we have p operator divided by 2m plus 1/2 of m omega squared q squared, which q and p, they don't commute. So the commutation of, usually I don't remember, let me drive this. So let's go with p and q. That is given by pq, of course, minus qp. Let's write it down. P is h bar divided by I, derivative with respect to q of q psi minus h bar divided by I, q psi. Then that is h bar divided by I, psi, okay, which is minus I h bar. Okay. And we know this. All right. No question regarding the simple harmonic oscillators? All right. So we do have this relation. And what I'm going to do, I'm going to drive the simple harmonic oscillators in such a way that you will see the same expression for the Hamiltonian as you see above. So now, in order to do so, I have to define new operators. Let's call them A and A dagger, which A is given by, I think for simplicity, I have written down some of those for ourselves. Okay. If we want to have a proper dimension, I think that's the way that we have to define this. 1 divided by square root of 2m omega h bar I omega, sorry, m omega should be the same dimension. M omega q plus IP. This is not the unique way, by the way. At the end of the lecture, we will define another one, which is dimensionless. Square root of 2m omega h bar m omega q minus IP. Okay. All right. So this is the these are the two operators that we defined them. I'm sure that you have seen that these two operators in the course of quantum mechanics, either advanced one or undergraduate one. But let's just review it for those people that they need to refresh their mind. All right, so from these two operators, I want to derive the Hamiltonian. Let's do the mathematics and calculate what is A dagger from these two expressions, assuming that P and Q is given by these relations. So they don't commute, and the commutation between P and Q is given by minus IH bar. Let's do the mathematics and do the calculation for A dagger. It will be 1 divided by 2m omega h bar, m omega q plus I p, and A dagger is given by m omega q minus IP. And if you look at the A dagger, A is given by 1 divided by 2m omega h bar m omega q minus IP m omega q plus IP. These are the relations that we do have. Let's simplify a little bit. A dagger will be given by 2m omega h bar. Then the expression will be m omega square q square minus I m omega q p minus p q. And finally, I get plus p square. And for A dagger A, I have 1 divided by 2m omega h bar, m square omega square q square plus I m omega q p minus p q plus p square. All right. I don't think that there is any mistakes. So if you look at sum of A dagger, A dagger, sum them up, plus A dagger A, we will end up with 1 divided by 2m omega h bar. Then we will end up with 2 of m square omega square q square plus p square. Okay. Good. A little bit of simplifications, then we will get these expressions. One divided by h bar omega, 1 divided by uh, 2m. Just a second, I will be back, guys. My apologies. Okay. So if we want to do this, how should we write it properly? 2m is here, 2m is there, that's fine. M h bar goes there. So I can write them as p squared divided by 2m plus 1/2 of m omega square q square is equal to 1/2 of h bar omega a dagger plus a dagger a. Is that all right? Yes. Okay. So essentially Hamiltonian that we had now in the form of a and a dagger is given by this expression. Good. And also I can look at a dagger minus a dagger a. I can look at the sum, I can look at the difference between these two. Then what it will be, the result will be, which one I'm subtracting from the other one is a dagger from this one. So it will be minus 2 im omega divided by 2m omega h bar. Then I have qp minus pq. Okay, qp minus pq is plus ih bar. So that should be minus 2im omega, and that will be ih bar divided by 2m omega h bar, which I multiply by this will be 1, 2 goes away with 2, m goes away with m, omega goes away with omega, it's equal to 1. So then it means that also here I have a dagger, which is equal to 1. The commutation relation between a and a dagger. Good. I think you got the point that there is a similarity between the Hamiltonian for simple harmonic oscillator and the Hamiltonian that you have it for electric and magnetic field. So we will write them down and let's get our conclusion here. And later, and after that, we will only talk about what is the property for a and a dagger. So just I want to have the feeling why we are doing this. Let's write down the Hamiltonian that we got it for simple harmonic oscillator, which is 1 divided by 2 h bar omega a dagger plus a dagger a. And from the other side for EM field, what we got for EM field per mode, one of the k vector, which I call it H for one of the k vector and one of the polarization. Someone can tell me, God, is H k square epsilon volume What else was in the expression?
Omega k squared.
Omega k squared. Excellent. And then we got a, k, and sigma, function of time, a, k, and sigma star plus a star of t, k, and sigma, a of k and sigma of time. Did I miss anything, guys? I have written only for 1k and 1 sigma. Then I have to sum over all of them. Is that correct? So now these two Hamiltonian for EM field inside of a box, remember that was EM field for inside of a box. With the dimension of L, L, and L, we got this expression. And a simple harmonic oscillator in the quantum mechanical language, which is this potential, is a one-dimensional thing. So if that's X or Q, that is the potential that you have it, which is a 1/2 of m omega squared q squared. Then these two, they are identical from a mathematical point of view. The only things that I have to do is replacing A and A star with operators. What are those operators? Are A hat, K, and sigma. And remember, also they can be time dependent, exactly what you have it for, like the harmonic oscillator. And that one will be replaced by A dagger of K and sigma and T. A dagger of K, sigma, and T. A, K, sigma, and T. And the only things that I have to do here is this term formally should be equal to this term. Okay? Let's do that. Then I consider AK power of 2 epsilon 0 volume omega k power of 2 should be equal to 1/2 of h bar omega of k. It should be the same mode, essentially. What is the freedom that I have it here? What is fixed, what is not fixed here?
AK isn't fixed.
Yes, tell me, Eric.
AK isn't fixed, I don't think.
Exactly. We had the freedom on AK, and we say that let's define AK later on. So this goes away with that, and then I will get AK power of 2 equal to h bar divided by 2 epsilon naught volume omega k. All right. Which we assume that AK is real quantity. Phase can be always attributed to the annihilation and creation operator, which I just talked about. So we can discuss about this, but for the time being, assume that it's positive value. So it's h bar divided by 2 epsilon naught v omega. Okay. Okay. Josh, you have a question? No?
I do not have a question.
Okay. I felt that.
Sorry, I actually was responding to an email. Sorry.
No worries. Okay. So then with this formal replacement, remember that we got AK, which was a freedom, and which was a free parameter, and I did not define that in the vector potential and electric field and magnetic field. That is given by h bar divided by 2 epsilon naught v omega k power of 1/2. With this, Hamiltonian for electric and magnetic field will be simply 1/2 of h bar omega k of a t k and sigma a k and sigma of t plus a dagger of k and sigma and time okay. So that is for electric and magnetic field for a specific mode of K with a polarization of sigma. So the total Hamiltonian essentially is given by the summation over K and sigma of H, K, and sigma. What does it mean? Can anyone tell me what we get for electric and magnetic field? Remember that we did not talk about A and A dagger. We know that A and A dagger, they don't commute. So this is the relation that you have it. So A, K, and sigma, and A, K, sigma dagger, that will be given by 1 and a K and sigma with any others will be commuting with 0. Maybe that one was better to write it in this formalism. K prime and sigma prime, that is delta of K and K prime, and delta of sigma and sigma prime. Okay. That is what we have to take care. And hereafter, we are extremely careful with placing A and A dagger, if they are from right or left. Okay, good. So can someone tells us that what is the meaning of these equations?
So our Hamiltonians for different Ks are all independent of each other, no?
They are all independent of each other, yes. So what does it mean? I mean, it tells us something. Josh?
I've got nothing.
You got nothing. Okay.
All modes are orthogonal.
They are
Orthogonal. Different modes are orthogonal to each other. Or?
No. They are. Look, in terms of modes, yes.
Is it like n-dimensional harmonic oscillator?
They are. Look like
N-dimensional harmonic oscillator.
n-dimensional harmonic oscillator. N-dimensional harmonic oscillator. Good point. Okay. What else? Nothing. Okay.
So like the energy from our Hamiltonian due to 1K is interacting with the energy of a Hamiltonian in another K. So these modes are
Interacting
not,
or does not interact?
does not interact.
Does not interact. Okay, good. All those three answers, they were correct. Okay, let's elaborate a little bit more on this. So now we found the similarity between electric field and magnetic field Hamiltonian with a simple harmonic oscillator. But we have to understand the physics better. I mean, this is just a formalism that people, they apply to do the field quantization. What I have done, essentially, I took vector potential, I took electric field, I took magnetic field, and I can trace all of them back to Hamiltonian. And what I found that the parameters that I induced there or introduced there, those parameters, they look like operators. But operators of what? Operators of simple harmonic oscillators, independent simple harmonic oscillators. Now we have to understand what is the meaning of those operators in the case of simple harmonic, and then we will go back and we'll say what is the relationship between those equations and between those A and A daggers in the Hamiltonian, in electric field, in magnetic field, in vector potential. Okay, let's do that. So we found that for now, again, we found the similarity, and now what we do, we go back again to simple harmonic oscillators. From the simple harmonic oscillators, we found that Hamiltonian is given by 1 divided by 2 h bar omega of A dagger plus A dagger A. And then we found that also A dagger minus A dagger A is given by 1, which is the commutation between A and A dagger. Now what we want to do, we want to understand what is the property of A and A dagger. Okay, good. Assuming that Hamiltonian is diagonalized in certain bases. Let's call this base n. So the basis of n we do have. So, and n is eigenstate of Hamiltonian. What does it mean that n, h acting on n is given by n, right? And what is the eigenvalue?
The energy?
Exactly. That will be energy associated to that state. Hamiltonian acting on a state which we assume that n in the base of n Hamiltonian is diagonalized, will be energy. All right, good. So as an exercise, h acting on n minus 1 will be En minus 1 of n minus 1. All right, good. So that is what I mean by eigenstate and eigenvalues. Now, do the mathematics and find what is h, A dagger acting on h. So find out what is A dagger acting on h, assuming that A and A dagger, they have this commutation relation. Let's expand it. Do it by yourself, and we will check it together. I'm doing also on my iPad, but don't look at the iPad. Do it for yourself, and let's. So, guys, okay, that's fine. Just pay attention here. Look at the mathematics that we should take care. So you have A dagger acting on H. All right. H is given by this expression. And we know very well that A and A dagger, they cannot be swapped. So A dagger is acting from left side on this expression. First, what I have done, I use this identity, replace a dagger. I replace a dagger with 1 plus a dagger a, then I got this expression. True? I get twice of a dagger a plus 1, and then again I have 1 divided by 2 h bar omega. Now, a dagger from left side is acting on this expression. True? So I will end up with a dagger a times plus a dagger divided by 2. And now what I want to do, I want to bring one of those a dagger to the right side, such a way that I can factor it out. Okay? So when I want to do that, so then I have to replace a dagger a with this expression, which again comes from the commutation relation. So a dagger minus a dagger a is equal to 1. Then I want to calculate a dagger a that is given by a dagger minus 1. And when you replace it inside of this, you will get this expression, which is h bar omega a dagger, which what I wanted explicitly, minus a dagger, which comes from this minus 1, plus a dagger divided by 2. We can keep it here, and that is what I need. So then I will write it down as h bar omega then I will get a dagger a plus 1 divided by 2. I will factor out an a dagger from right side. Then I have another expression, which is minus h bar omega a dagger. Do you agree with this statement? Is it clear what I'm going to do? What is this?
Yes. Hamiltonian.
Is Hamiltonian. So is Hamiltonian a dagger minus h bar omega a dagger. All right. So now I am doing, let's look at the expression that we had it for Hamiltonian. Hamiltonian acting on state of n is given the energy of the state of n. Now I multiply both sides from left by an a dagger. Then I will get a dagger h acting on n equal to a dagger energy of n acting on n. Okay? And from here, only I look at the expression for this side, I got a dagger h acting on n is equal to h a dagger minus h bar omega a dagger acting on n. True? I just replaced this, which I got it from this expression. All right. So h minus h bar omega A dagger acting on N. I factor out A dagger from right side now, and I got this expression. All right. So from left side, A dagger acting on H on N is this expression. And from right side, it is this expression. Okay. So I have H minus H bar omega acting on A dagger N is equal to En A dagger acting on N. So H acting on A dagger N is equal to En plus H bar omega acting on A dagger N. So can someone tell me what is the meaning?
That A dagger N is an energy state of the Hamiltonian with an energy level that is H bar omega higher than En.
Exactly. So we get this relation that A dagger N is an eigen state of Hamiltonian. Right? What is the eigenvalue? Is En plus H bar omega. So it seems that A dagger acting on N will bring the energy level, as Josh say, by H bar omega higher. Okay? So if that is the energy level that you have it for the state of N, then it seems that A dagger will bring this energy to N plus 1, which the difference between the two levels of energy is H bar omega. All right? Is it clear, guys? Good. So it means that A dagger N is proportional to N plus 1 state, which I have to find out what is this proportionality coefficient. So let's call it A dagger N is equal to, let's call it, should I call it C? Yes. C N of N plus 1. Okay. In a similar fashion, take Hn equal to En n, multiply both sides by A from left side, do the same calculation, then you will end up with this expression, which is Hamiltonian acting on An will be equal to energy of N minus H bar omega A N. Okay, so let me bring it to the other side. Good. Okay. So what does it mean? Let's ask someone else. Ben, you're auditing the course. Let me ask you.
So basically means you lower it by energy H bar omega now?
Yes. So it means that if I take A operator on state of n, I will bring it lower by an energy which is h bar omega, and that's the action of A. So we call A and A dagger ladder operators. Okay? Ladder operators. And remember, A acting on n will give you n-1 state, which I don't know the coefficient of dn. We will find all of them.
Ibrahim, do you mind just, I think I missed it, but explaining how either of the ladder operators, but where you get this proportionality, like A dagger on n is proportional to n plus 1? Like how we can infer.
Look at the right side of the expression. So let me highlight one of them. Let's look at this one, okay? So if you look at this expression, what you will see that A dagger n has an energy which is higher from En just only by h bar omega. Right? So it means that instead of this energy of En, which you have it, now you have a state which is given by this, which the energy of this state is En plus h bar omega. That's the reason that we call it another state, which is a higher one.
Yeah. Now I see.
Okay. And the same scenario for -1 with A. You will see later on that A and A dagger, they will be called also annihilation and creation operator. Okay, when we talk about mode explicitly. In the simple harmonic oscillators concept, people, they call them ladder operators. They bring up and down the energy. But in the concept of modes, we call them annihilation and creation mode. I think my grant supervisor called destructive, I think, destructive operator. Anyway, any questions so far, or all is okay? Good. So if we are okay, then there is a valid question for a simple harmonic oscillator. What is the ground state? Simple harmonic oscillator, you have this parabolic energy, let's say potential. Then a valid question will be, what is the energy, minimum energy that you will get it for the modes there, for the harmonic oscillator there? What is the minimum energy that in principle you should have is 0 energy, because the potential is positive. Okay, zero, larger than 0. So now the question is that what is the ground state? Ground state is a state that you cannot go lower than this. Okay, so it means that A acting on n, let's say the ground state, let's call the ground state as with 0, will be 0. This is the condition that you have it for ground state. Ground state condition. I cannot bring it lower than this. All right. What is the Hamiltonian of A0? Oh, let's say, just not going with that, even simpler than this. What is the Hamiltonian of 0? It is h bar omega A dagger A, right? Let's look at the expression. Yes. Plus 1/2 on 0. What you will get for this? Is given by h bar divided by 2. So ground state energy is h bar omega divided by 2. All right? Because A acting on 0 will be 0. Okay, fine. So now look at this interesting property that we have. It's a simple harmonic oscillator. So that is the potential that we have. Is the potential of 1/2 of m omega squared q2. And the energy that we have, this is the level of energy, is 0 energy. Oh, let's say, call it 0. Now, the ground state, which is n equal to 0, does not start from 0. It starts from a higher one, which what is the level of this is 1/2 of h bar omega. It will never start from this energy equal to 0, which is extremely important. What about the second one? Is n equal to 1? What is the difference of energy between these two? Let's go with a better picture. If it's 1, 2, 1, 2, 3, 4, is n equal to 1. This is the energy, which is h bar omega divided by 2, and that is 3 h bar divided by 2 from the beginning. And the other one is n equal to 2, which is 5 h bar omega divided by 2. And what is the maximum energy? We don't have any limit for the maximum energy. Can go as high as you wish. And the ladder operators just bring them up and down between these levels of energy. All right? Good. So states are normalized to 1. What does it mean that n is equal to 1? I choose the coefficients, and this is algebraic. This is a algebraic approach. So if someone wants to really go with the differential equation, of course you can do that. Even from this, you can find the representation of those states in the position space. So someone can look at the operators and just do transform from algebraic approach to the position representation, and you can find the explicit expression for Hamiltonians. For eigenstates. So states are normalized. This is true also for n minus 1, n minus 1, and also for n plus 1 and n plus 1. All of them, they are normalized to 1, is what I have chosen. And what I know from also, it is clear from this expression and from the ladder operator that energy at the state of n is given by n plus 1 divided by 2 of h bar omega. Okay. So as you see, for energy of 0, it's given by h bar divided by omega. H bar times omega divided by 2. For energy of 1, it's given by 3 h bar omega divided by 2, and etc. Here, I can define an operator, which I call it number operator. And what is the action of this number operator? Acting on state of n will give me n. And number operator that I have is a dagger a in my calculation. If you look at the Hamiltonian. So essentially, Hamiltonian that I have is given by n operator plus 1/2 of h bar omega. Questions? Now I have to find out what is the expression for a dagger acting on n and a acting on n. Do you remember that? So we say that a acting on n will be given by dn n minus 1, and a dagger acting on n will bring you to, did I say c and d? Yes, that's true. cn n plus 1. Good. Okay, as an exercise at home, using the above expression that I had it, show that a acting on n is given square root of n times n minus 1, and a dagger acting on n will give you square root of n plus 1 times n plus 1. All right. Is it difficult or no? Should I do the first one? Okay. So what is a dagger n, a on n? Is the number operator that will give you n. Multiply both sides by bra of n, which is n. So that will be number of n and bracket of n, which is equal to 1. So it's n. And a acting on n will give you d, and A dagger acting on N, the bra of N will give you D star. So that will be dN square equal to N. And from this, you will get dN equal to square root of N. Of course, there is a phase which always we put the phase inside of other parameters that we have. So for the time being, it's okay. Okay, so in a similar fashion, you can prove that A dagger acting on N will be given you square root of N plus 1 times N plus 1. All right, I think we reviewed simple harmonic oscillators properly. And now we have to go and look at electric field and magnetic field and Hamiltonian for the modes that we have. So, sorry. Now, the question that we had was this box. And we say that for this box with the dimension of L, L, and L, now we have electric field and magnetic field propagating in any other directions. So, and for this, we found that the Hamiltonian essentially is given by summation of K sigma 1/2 of, should I go 1/2? Yeah, let's go with a simple one. Yeah, let's go with 1/2 for the time being, and then we can write it down. H bar omega K and A K sigma A dagger K and sigma plus A dagger K and sigma. A, K, and sigma. Okay. Remember that those are time dependent, but I will not write them down. Okay. And if you want to use the commutation relation that we propose, then now you can write it as summation of K and sigma of H bar omega A dagger K and sigma A of K and sigma plus 1/2, which we used the following commutation relation, which is A K and sigma and A dagger of K and sigma is equal to 1. Oh, let's write it in proper way. K prime delta prime is delta of K prime delta of sigma prime. All right. Now you can tell me, with this expression that we had it for the simple harmonic oscillators, can you tell me now what is A and A dagger? Anyone? Valerio, do you have any thoughts? I can
ask in which creation and annihilation operator?
Creation and annihilation operator for what?
For modes.
Modes of
the field.
Exactly. Exactly. So now we are not dealing with simple harmonic oscillators. We use that analogy, and now we found that Hamiltonian for electromagnetic field is given by annihilation and creation operator. So what are those creation and annihilation operator? They are creating the field for you. They are creating the field, EM field. So let's say that we do have vacuum. What is vacuum?
The absence of any stuff.
Who is speaking?
Me, Manuel.
Manuel. The absence of
anything.
Any here in this concept.
In this context is the absence of modes. I mean,
the absence of EM field.
Okay.
Yeah, the absence of EM field. So which is given by 0. We call it 0. Okay, this is our vacuum. And can you tell me what is Hamiltonian acting on vacuum? Which is 0 essentially.
1/2 h bar omega.
1/2 of summation. Don't forget the summation. This is important. Okay, sigma 1/2 of h bar omega. Huh. And of course, remember that omega is function of k. Right? So it is summation over I have to write it in this way, 0, which is summation over k, summation over sigma, 1/2 of h bar omega, 0. So what is the summation over sigma? Nazanin? Is this function of sigma?
No.
No. Okay. The summation on sigma. How many parameters do we have for sigma?
2.
2.
Sigma
Okay.
1.
Exactly. So that will be summation over k of h bar omega k of 0.
Yeah.
So what is the energy of vacuum?
It's like
All right. Is this converging or diverging?
It looks really, really diverging.
Exactly. It is diverging dramatically. Okay. So remember, for single polarization is 1/2 of h bar omega. But since we do have both polarization, then it will be h bar omega per mode. How many modes do we have in, I mean, how many k vectors do we have here? Infinite. Because the k was given by boundary condition. Do you remember that? K was given by 2 pi divided by L times n, which was n1, n2, and n3 for x, y, and z. So essentially, I think people, I'm sure that you are familiar, but if you are not, then I can drive these for you. The summation over k can be simply replaced by can be replaced by 2 pi divided by L power of 3 integral of dn. Okay, d3n. So if you do the integral on this, then it's terribly diverging. It's not a converging point. So the conclusion is that vacuum has an infinite energy. How many of you remember ether? The concept of ether. No one remembers these?
Yeah, it was a material that light travels through. That they.
Yes. So people in 18th and 19th century, they believed that the entire of the universe is filled with ether, which allows light to be propagating inside. Michelson proposed that experiment. I mean, Michelson-Morley experiment, you know about the interferometer. They proposed that interferometer to reveal the presence of ether. And it seems that somehow vacuum has this property that it has an infinite energy and it covers the entire universe. And you will see later on, I mean, not in this course, I mean, during your career, you will see that vacuum has an interesting property which allows you to create particle and antiparticle and annihilate them in a very short time. So it's made of particle and antiparticle at the same time, which in an extremely, extremely short time, those particles are created, and again, they will annihilate. Okay? So, and that's a reason that it has an infinite energy. And of course, some experiments are proposed, and some experiments have been observed in the laboratory, which you can see the effect of vacuum there. So I will encourage you to read about Lamb shift. Okay, so it's inside of your book. Go and read it. Is Lamb shift. Read that one, and that's one of the evidence of having ether. Sorry, okay, so they call it vacuum. I will call it, is a taboo for those people that they prefer French. So it's a taboo among physicists that they don't call it ether, they call it vacuum. They feel a little bit better. So it's up to you. Let's call it vacuum. And vacuum has infinite energy, and it can be revealed in many different experiments. One of them is a Lamb shift, which I think Lamb got the Nobel Prize for observing this in the laboratory. And many scientists, they believe that this observation was a turning point in the field of quantum electrodynamics. So that many scientists, many great scientists, they thought about quantum mechanics, and they thought about the field and the condition of the field, and they see, yes, vacuum has an infinite energy, or vacuum presence and having an effect in the system. So let me give you, I will give you another example at the beginning of next lecture, which is Kazmir effect. So I will explain you that you can have the effect of vacuum when you have two very thin plates. So if you get two thin plates of a paper, for example, if you keep them close to each other in vacuum without any forces, these two plates, depending on the material, assuming that these are conducting materials, they start to attract each other. So they start to feel a force which keeps them together. And this is one of the evidence that you have a vacuum which contains energy and has field inside. Let me give you just a hint that you can go home and think that they cheat, and they were not so explicit when they taught you quantum mechanics. Okay, assuming simple two-level atom system. Okay, two-level atomic system. An atom with two-level energy. Which one of them is ground state? The other one is excited state. Okay? And we know that you can follow the Schrodinger equation and you can find the state and etc. Assuming that the state is in the ground state at the time equal to 0. What is happening? And of course, I know that this is the energy level, E equal to 0. What is happening at the G at the time of t? It is given by exponential of minus I omega t, right? Which is energy of G divided by h bar times t, acting on ground state at the time of 0. Do you agree with me? Do you remember this? This comes from the Schrodinger equation. It's just two-level atom, a two-level system. What is happening about exciting system? At the time of 0, we believe that it's in excited state. Then at the time of t, what is happening with this? Do you agree? The same scenario. So now I'm asking you a question related to the physics. I have a two-level atom system. I'm doing excitation. I excite the atom. What is happening? Will the atom decay? I'm exciting an atom. Will the atom decay?
No, it's gonna stay in the state that it was.
Yeah, this is what you're telling me based on this expression, right?
Yeah.
But in experiment, is that true?
No.
No.
It's gonna. No.
Exactly. So if you look at this expression, you will see that E and G, they are orthogonal to each other. There are two different levels. But even at any given time of t, they are orthogonal to each other. However, in experiment, what I will see in experiment, I see that E at given time of t will decay to the ground state as well, and has a probability of being in the ground state or being in the excited state. So there is something wrong with this expression that we had it. This expression did not include the action of vacuum in our calculation. You have to have the action of vacuum in order to see spontaneous emission. Okay? When you excite an atom, then the decay will happen, and this decay was entered by Einstein empirically into the equation by A and B coefficients. But we know that if we believe in quantum mechanics, the first quantization will not give us these. Then what you have to do the electric field and magnetic field quantization, and you understand that electric field and magnetic field quantization, even when there is no electric field and magnetic field, still vacuum has energy, and this energy plays a role here and will give you the decay. Okay? So with this, I will close the lecture today. And next lecture, briefly, I will tell you about Kazmir Effect. I will not go into deep mathematics. If someone wants, we can have a discussion afterward. I will drive the Kazmir force, and you will see that also vacuum will be manifested in that calculation, and you will see the effect of vacuum there. I will encourage you to read about Lamb shift. Since Lamb shift is given inside of your book, that's a reason that I'm not talking about that. But it's an extremely, extremely important experiment that you should learn about that. Okay? So I will close the lecture, and now I'm stopping the recording, and then we can discuss.